Hello everyone, let's discuss the computation of particle paths using interpolation. First, let's state the problem. We want to solve dx by dt is equal to u of x with initial condition x of 0 is equal to x0 where x0 is given. Now, let's state a first issue we may encounter. Having chosen a step length h for our numerical method, to proceed in theory, we would need to be able to compute u of x at an arbitrary value of x. In practice, there may be difficulties with this. For example, we may only have fragmentary or partial information about the velocity field u of x. So we might know u of xk at discrete points xk where k goes from 1, 2, 3, etc. To be able to construct a particle path using an arbitrary step length h, we need some means of estimating u of x at points where x does not equal xk. Next, let's discuss another issue we may encounter. We might have available an approximate path xk, computed using Euler's method, and wish to construct a continuous curve passing through all points xk to create a smooth representation of the particle path. Mathematically, this is the same as the first issue, as they are both problems of interpolation. Then, let's define interpolation. Interpolation is inferring information about a function at an arbitrary point given information at a sequence of points. Let us suppose then that we only know the velocity u of x at a sequence of n+1 points, also called nodes, xk, where k goes from 1 to n+1. That is, we know uk, where uk is equal to u of xk for k going from 1 to n+1. We want to infer information about all u points at all x points given the initial data values. Following on, let's mention using interpolating polynomials. Our goal is to compute a polynomial passing through all nodes, which we can use to approximate the values of u between the nodes. In general, we need an nth degree polynomial to interpolate n+1 points. An nth degree polynomial has the general form p sub n of x equals a1x to the n plus a2x to the n minus 1 all the way up to an+1 with n+1 unknown coefficients a1 to an+1. At each node xj, we enforce the condition p sub n of xj is equal to u of xj and use the polynomial to interpolate values for u between the nodes. Now, let's discuss the direct approach. In a direct approach, we simply write out the equations p sub n of xj is equal to u of xj explicitly. But this is just a linear system of the form v dot a equals u, where matrix V is given by this matrix, the solution vector to be found is given by this matrix, and the right hand side vector u is given by this matrix. The matrix V is called the van der Mode matrix. Next, let's state a theorem for these results. Given n+1 points x1, x2 all the way up to xn+1, and n+1 values u1, u2 all the way up to un+1, there exists a unique polynomial p sub n of x for which p sub n of xj is equal to u of xj, which holds for j is equal to 1 up to n+1. Then, let's discuss the drawbacks of using the direct approach. Suppose we fix the positions of the end nodes at x1 equals 0 and xn+1 equals 1, and then increase the total number of nodes. When we do this, the nodes become more bunched, and the spacing between successive nodes, xi minus xi plus 1, goes down. Since the modulus of the determinant of the matrix V is equal to the product from j equals 1 to n times the product for I greater than j up to n of xi minus xj, this means that the determinant of V decreases and the matrix becomes nearly singular and the system becomes ill-conditioned. Ill-conditioned systems lead to large round-off errors when a solution is calculated, for example using Gaussian elimination. Also, the system is sensitive to small perturbations. Instead, let's discuss Lagrange interpolating polynomials. We introduce the nth degree jth Lagrange polynomial Lj of x which is to be constructed so that j equals 0 at all nodes xi with I not equal to j, and lj equals 1 at node xj. So lj of x is equal to the product from k equals 1 to n plus 1 without k equaling j of x minus xk divided by the product from k equals 1 to n plus 1 without k equaling j of xj minus xk. Lagrange's interpolating polynomials is given by the linear expansion Pn of x is equal to the sum from j equals 1 to n plus 1 of u of xj times lj of x. Clearly, p sub n of xj equals u of xj, so p sub n takes the values of f at the nodes. Note that p sub n of x is the same polynomial as the one obtained by using direct approach because the polynomial interpolating a set of points is unique. And, as ever, thank you for watching.